Okay, so before I start, I just want to mention, both Gray and Josh mentioned that I work at Excel, which is our gold sponsor here this year. Before people think I bought my way on this stage, I've also been an organizer here for 10 years, so I'm up here the proper way. I strong-armed Gray into it. And then I strong-armed my employer to sponsor, so here we are. So this is a look at the Crystal programming language. And I want to give the context of why I even thought to look at it in the first place. Josh mentioned that I run a nonprofit in Loudoun County called Loudoun Codes, where I teach K-12 computer science education. In fact, if you were here last year, you saw 2 of my students speak. They've been at the event regularly for the past few years. I have 2 here today. And teaching K-12 computer science education is amazing. I think I miss my life's calling not being a teacher. Of course, I'd have to move out of Loudoun County to teach in Loudoun County, which is a sad story about teachers. So, or how we value teachers. But in teaching students, especially at the high school level, we teach Java at the high school level because the AP exam is in Java. And they do need to learn the fundamentals and the concepts, but I often show my students concepts in Ruby. And at first they're like, they don't even realize it's a language, then I actually run it, and then they'll accuse me of cheating, right? They have to, actually have a variable and have a loop, and we can just say .each. Right? They have to have 3 inner loops to find all combinations of 3 things, and I can just say combination 3. So I love Ruby. But in teaching computer science, we're often talking about the efficiency of computation and algorithms, and of course Java beats, hands down, on those kinds of algorithms. So I'm often like writing something for clarity in Ruby, and then wishing I could make it faster to express a point. Let me tell you a bit about our MacGuffin that we're going to talk about today. That's why I looked at Ruby. But today we're going to talk about something I wrote last year for Papers We Love. This is a group. Is Lee here? We have a Papers We Love here in Washington, D.C. And Lee, the organizer, asked me to speak at the meeting last October-ish. She gave me about 6 months' notice, and I was like, cool, that's a lot of time for me to research a good topic. So I did what every good nerd would do. I went to my standard issue copy of Selected Papers on Discrete Mathematics, and I started reading, right? And I got to the very first paper, and I found this problem that has captivated me for the last year. The concept is called mutually orthogonal Latin square. And you might know it. It's often a little card game, right? Take all the face cards from a deck of cards and try to arrange them so that every row and every column contains 1 face value and 1 suit. And that is one solution. Right? If you notice in this suit, there's only one, like this row only has 1 ace, it only has 1 heart, only 1 queen, only 1 spade, in every row and column. And here's an interesting question: how many solutions are there? And the first paper in Knuth's Selected Papers on Discrete Mathematics goes into this problem, goes into all kinds of variations on the problem, and it talks specifically about Latin squares of order 10. So I can give kids a deck of cards, and they can find a solution in about 20 minutes to this. Imagine doing it with 10 by 10, right? The story here is that Euler, who was fascinated with the same problem, proved that there were no Latin squares of order 6. There are none of order 2. By the way, this is an order 4. Right? And he hypothesized that there were none of order 10. And that held until 1963, when a computer found the first order 10. And until then, Knuth's paper mentioned that even with the available computers we have today, it didn't seem like it was a solvable problem until somebody found a clever algorithm, and then he didn't go into the algorithm at all. And suddenly I was fascinated. I needed to know what this algorithm was. But to tell you one thing about the way Latin squares work is that you can take any row and column and switch it, and it's still a solved Latin square. The constraint here isn't in any row or column, right? In fact, it's a little bit harder to visualize. But if I could keep the suits the same and swap like the aces with the kings, it's still a solved problem. So in finding one solution, we've actually found about 144. Of course, with larger combinations, there's more to solve. In fact, here's a child's game that is a 5x5 version. In fact, I have a version of this over at the table if people want to play with it at lunch. This is the paper that Knuth mentioned. It's Computer Investigation of Orthogonal Latin Squares of Order 10. Published in 1963, and it would take about 40 hours for it to find a Latin square of order 10, running on a UNIVAC 1206 military computer, whatever the heck that is. Now the story for me getting this paper, I searched online, couldn't find it online, although you can find 4 references to it in other papers. Went to the library, searched, went to the neighboring county's library, searched their system, couldn't find anything. So I went to my librarian and said, I'm looking for this paper. I had all the credentials, what book it was in, who the author was, the year it was published, conference that it was presented at, and I gave her all this information. 2 days later, I got it emailed to me as a PDF with the instructions to stop by the library and pay $3.40 for the research they did. And I was like, that's awesome, right? So support your local libraries. They're still very relevant. So the paper was not at all easy to read. This might be the hardest, geekiest thing I've ever done for fun, was digesting this paper, because it is not a straightforward explanation of the algorithm either. It talks a little bit about the flawed algorithm, which we can talk about, but I'm going to save some time here. We can talk about it at lunch if you want, versus the optimized solution he found to it. And it's an amazing problem of refactoring, not in like the code sense that we've usurped that idea for, but actually the concept of taking a huge combinatorial that would take forever to search, and the naive implementation factors it like down by an order of 10, but the algorithm we have cuts it in half. So it's now solvable in 40 hours in 1963. I wanted to know how fast Ruby could solve this, right? Here's the first one my Ruby program ever found. Now I'm expressing it as numbers and letters, but another way to express this is every combination of letter and number here occurs exactly once. And every letter and every number occurs in a row and column exactly once. When these were discovered in 1963, the whole class was called Euler busters, because they proved Euler's theorem wrong here about Latin squares of order 10, that they didn't exist. My Ruby program, single-threaded on my machine, finds one, depending on the search space, every 2 to 5 minutes. Crank it along. And of course, Ruby single-threaded, with my machine with 8 cores, I could open 8 shells and create 8 versions of it, and they start cranking out. I can find one about every 30 seconds. And it made me think, Ruby, that's decent performance. I wish Ruby was multi-threaded so I could do some cool stuff with it. But how fast would that be in Java? And I started looking at how I would do it in Java, and the code got ugly really quick because I'm using combinations all over the place, and I really didn't want to translate it to Java. So I looked at using JRuby for a little bit and ho-hum. And I love JRuby. It just wasn't a good fit for what I wanted to do, because then you have to do real multi-threading, you have to mix in Java's classes in with JRuby, and it's a little faster in JRuby, just natively. So I started looking at Crystal. This was Ben Miller, are you here? Yeah, Ben turned me on to this at a Ruby Loco meeting last summer. And Crystal, let me explain what Crystal's about. Crystal is a language inspired by Ruby. It does not have a goal of API compatibility, so it's not perfect. Right? It's a compiled language. And I know a lot of us here may have never worked in a compiled language. Let me try to make this a simple concept. A compiler is kind of like every unit test that the person who designed the language could have thought to write about your program, not knowing anything about your program. It proves some level of correctness, right? And the level of correctness depends on the language and some of the other abilities of the language. But a major point of compiled language is relying on a type system. This is why in Java we have to say, that's a string, that's an integer, that's a version of this class. And one of the reasons why we get some cool abilities like interfaces, but we also end up with very verbose stuff and problems where we end up with complex situations, and then when they totally borked the Java language with adding generics to it, was a pollution of the type system. And I didn't think I was going to like Crystal because of that experience. I think I'm wavering on that, and you'll see here. Really interesting, it has these null checks and guards. I can define a variable. In fact, if I just define a variable as its normal type, it can never be nil. I cannot have a variable that is nil. So gone are the null pointer exceptions that just kind of crap out your app in the middle of it. You have to specifically say, yeah, it's cool that that's a nil there. And we'll look at that today too. There's a concurrency model like Go. It's not parallelized yet, which that's a longer topic that I can fill in 20 minutes. It also supports a heck of a lot more. There's some really cool features in this language. We'll talk about that. So we'll talk about why I would use it after we see the example. Here is my mutually orthogonal Latin square program in Ruby. And I'm not going to go into a huge amount of detail with this. But it's 180 lines of Ruby code. And what I'm doing here is I'm defining an array of any size, because I can find them of different sizes, define a 2D array. And then I just start finding Latin squares, the first level Latin square that fits. And when it finds one, it prints out a dot and then searches the space to see if there are any orthogonal versions of that. And the search space is huge, right? So the sooner we can find that, oh, it's not possible in this space, the sooner we can abandon that thread and find another one. I have this little pretty print. Once it finds one, it prints out the letters, gets the letters, does this each with index, printing over, prints out something. We have this concept of reconstituting because there's a place where I need just the indexes. Square, this is where it does a recursive. Notice square calls itself as it is sitting here searching through the space. It says, okay, that fits in that row, that fits in that row, that fits in that row. Oh, no, it doesn't, so it pops back and keeps searching. Typical depth first search there. We test to see if we're valid. Right. We create these concept of candidate groups. And that is a higher level concept. But the naive algorithm, actually, let me pull up my slide really quick. I think I'll have the time to cover this. The naive version of the algorithm says, okay, so I find the first Latin square. Let's say that's just the letters. Notice, here's another point. Notice that the letters across the top are A, B, C, D, E, F, G, H, I, J. Because I can rearrange those columns in any order, we can rearrange them so the first one is just always in order. And we can also arrange one of the two things along the row side here so that it's in order. This is called its fully reduced form. And this is how, if we find two Latin squares, we can see that they're equal. We put them in the reduced form, are they a match? Then they're the same square. The major optimization here is just searching for the reduced form. So, okay, I find a Latin square, which is like the second row, B, H, I, F, J. It finds a Latin square. The naive implementation of the algorithm is saying, okay, let's find every path that includes just the A's. So A. And now let's try to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in there. And let's find all the B's. And then let's find every combination of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 that still works. And you search down that way. That's the naive implementation that will never compute by the end of the universe. The other algorithm, which seems like this would be horribly worse, is let's find every path through here, where instead of saying all the A's, let's find every path that goes, A, B, C, D, E, F, G, H, I, J, or A, B, C, D, E, F, G, H, I, J, for every row. These are what it calls the transversals. And it finds a huge number of those. But because we're operating in a larger space on this side, the space on the other side of the equation ends up much smaller. It's kind of like if we have 1,000,000 things, we can call that either 10 times 100,000, or we can call it 1,000 times 1,000. It would be so much easier to search through 1,000 things 1,000 times when we can end earlier than 100,000 things 10 times is the idea here. That's the rough gist of the optimization here. As you can see here, there's a lot going on. I'm injecting, I'm doing permutations, right? So I need to find all these candidate groups, then I sort them into the number they start with so I can search just the reduced form. There's all kinds of complex code here. We find all the transversals, we start iterating, we convert, We find all the transversal groups form. We test to see if a square is valid, right? We do this orthogonal search. Once we find the main one, we do the orthogonal search. And then this is the meat of where the algorithm starts. We grab the order we're searching for the first command line argument, the second for the finish, the total number we found so far, and we start solving. Right? So we solve, and then every square that solve finds, we call this code. So for every square, we yield and search for all the orthogonals for that square. If it's unorthogonal, we reconstitute it for display and then pretty print it. That's understandable. Right? Let's watch it in action. I can come over here and I can say Ruby moles.rb. Let's find all of them for order 4, right? And the number I need to find. Well, let's see if there are 100 of them. Moles. Moles.rb, order 4. Let's see if there are 100 of them. Believe it or not, there are only 2 valid solutions. Now, of course, you can find 144 permutations of each, but there are only 2 valid solutions if you sit down with a deck of cards to do this. What about order 5, the little puzzle I have over there? Oh, there are a lot of them. Every dot here is a square that didn't find a solution. And then we hit a square, and then we found 3 of them. That's interesting. So now, finding 5 seems to go pretty fast. There are none of order 6, so I won't even try. Let's say order 7. Oh, notice those dots are going by a little slower now. Right? There's time involved. In fact, we didn't find any. They're out there, but they're rarer. Let's try order 8. Notice how slow that dot's going now? I'm surprised it's not finding any. There should be 1 in there. Let's try order 9. Lot slower. I'm going to fire up order 10 and let it go while I do the rest of my talk. We'll come back to that one. We'll open another window, and we're going to come up a level. We'll look at the Crystal version of that in just a second. But 180 lines of pretty computationally intensive Ruby, that sounds like that's going to be hard to convert if the language is just inspired by Ruby, right? That I have to add types to and all that messy stuff. We'll come back to that. Let's look at the things we need to know about Crystal to know this language. I'm going to cat out an arrays.cr file. Right now, this is the Ruby version, right? I can say numbers, skip this line for now. I can put numbers into 5, put 5 into numbers, 8 into numbers, and then I can say puts. So let's run that. We'll do a Ruby on the arrays.cr, which is strange, but it'll work. 5 to 8. Okay, so let's compile that now. With Crystal, we have to compile. So I'm going to say Crystal build arrays.cr. And it says, syntax error in arrays.cr too. For empty strings, use of element type. Let me open that file and explain what's going on. I'm going to comment out the Ruby version. In Crystal, it will infer the type whenever it can. But when I just say numbers, hey, here's an array of stuff, it has no idea what it is. So I need to teach it. I need to say, this is an array of int 32. We comment that out. It's no longer valid Ruby, or we uncomment that. It's no longer valid Ruby, but I can now build it. I type. Notice I don't need to prefix it with Ruby because now it's just a compiled binary. I can run arrays, and that was so much faster. It's awesome. Well, yeah. Okay, let's look at a few more syntax highlights, and then we'll see how much faster things are. Let me look at combined inference. Let me clear. Cat combined inference. So an interesting thing about this is that, much like Ruby, I can switch types on the fly, right? I'm going to select a random number here. Message is a string over there, message is a 10 over there, then we're going to puts the message, and puts type of the message. Haha, that would confuse the heck out of Java, right? We would have to say, no, message is either a string or an integer. right? We can't have it both ways. We can't have our string and add it to, whatever. But let me show you what that type of prints out. I'm going to say crystal, build. What was the name of that?
Spell it right. You need a D. D for build.
Combined inference.
Thank you. So we build it, we run it, and Ruby says, hello world, because that's the one that won the random number. But parsing that code, the compiler figured out that at this point in the code, this thing is either an int32 or a string. So in writing this in Java, I'd have to say that's either an integer or a string. It can't be both. In Crystal, it can be both. As long as you treat it polymorphically every place back there, it kind of automatically backfills and figures out, yeah, there's an interface, we can use this stuff. This compiles. That's a huge level of safety that we got from that compile step. And it just figured it out for my code. So most of the time we don't have to declare a type. Sometimes we do. Let me show you nil handling. Cat nil1, CR. I have my hello message again, and I'm going to assign nil and try to print it out. Let's see what happens here, because I said that things can't be nil. Crystal build nil1.cr. That seemed to work. So let's do a nil1 and see what's going on. Again, we can switch types, and nil is actually a type here, right? So we can print hello world as a string, and we try to print out a nil, we get nothing, and it tells us it's a nil. Let me clear that and run that again so we see it up for everybody in the back. So hello world's a string, and then we print out nil, which is empty, and then we print out the type as nil. So that seems to work. That doesn't seem to have added much safety yet. So let's look at nil2. So I'm doing my same thing here where I define an array of int32 and I start putting integers in it. What happens if I try to put a nil in there? Crystal build nil2.cr. The compiler says you can't do that. That's an array of integers. You can't put a nil in there. So a little bit of type safety. Let's fix that. Because I know what I'm doing. I want a nil to be able to be in there. So we're not of int32 anymore. We're int32 question mark. And now I've turned on basically type in safety here. I'm saying, no, I'm going to allow that to be nil. We build it, and that seems to work just fine. I run it. Nil2, yep. And it says, okay, nil's in that array. We're happy with that. Clear and do it again. 5, 8, and nil. So we've turned on the ability to have nil in that array. We now know enough to come over here to my moles presentation, my moles code, and compare. So let me do a diff of the moles.rb version and the moles.cr version. And let's pipe that into TextMate. And let's look at the differences. Where I previously just had an array that I made new in Ruby, here I have to say it's an array of int32, and I have to declare its size. So that's not horrible, right? Let's keep looking at some of this. Over here, this is interesting syntax. On this line, because I have a block that I take, I have to tell it, we pass this block in an array of int32, and we don't care what we return. That's what the underscore means. The API is not exactly the same. In Ruby we have include, here we have includes. Right? Here we have an inject versus a reduce, permutation versus permutations. Minor differences, right? There's some type stuff in here. Array of int32. Wow, that seems ugly. And truthfully, this is one of the hard things about doing this in Ruby as well, is that I have my row that I'm looking for, which is an array of integers. And then I have that as a square, which is an array of things. And then I have an array of those, which are all the candidates of all the squares, of all the rows, of all the... And we're going to look at how type actually helps us with that. Right? But these changes are not really that dramatic. Everything's about just keeping some maintenance on arrays and defining what blocks return. But there's one other trick up my sleeve. In that after I learned how to convert it, and actually started looking at what it means to be idiomatic in Crystal, I created a second version. I define at the top a line as an array of int32, and a Latin square as an array of lines. Notice these are not classes. I'm creating my own types in the type system. And then before, where I had an array of int32s, I can now say, no, that's just a Latin square. So I've added a little DSL around types, not just classes, but types. When you were learning Ruby, did you ever look at a method and be like, I have no idea what I need to pass into that? It's a bunch of named things, but I don't know what they are. Right? Is that expecting a URL or a string or whatever? That returns something to me, but I don't know what it is. So you actually write your code and do a little, what is that class of that return type? So with this, Crystal is making me document some of those assumptions. That actually makes it a little better teaching language in some ways as well. That's kind of useful, right? But the point here, I have 180 lines of some pretty algorithmically complex stuff. The first version changed about 18 of those with minor type inference rules. The next version cleans up some of those lines by actually allowing me to create my own types. So what do we get for that effort? Over here, I'm going to, just so I have nothing on my sleeve, I'm going to say Crystal build moles2, build a Ruby version of that, or build a Crystal version of that. And now I can do the same thing. I can say moles2, let's find all the ones of order, I don't know, we tried 7 before and didn't find any, right? Let's see what we get here. Oh, we found one. That's, yeah. So let's try 9. 9 was the one that ticked by pretty slow before. It still seems pretty slow. Let's horse race it, right? Let's just try 10. Time it out. 3, 4, 5, 6, 7, 8, 9, 10. That took 10 seconds of CPU time. Well, 10 seconds total. So now let's do the time of the Ruby. Time Ruby of moles.rb with 9 and 10.
That's moles.
Mole. Thank you. And this will take 20 or 30 seconds. We'll come back to that. Now, sure, I have other stuff going on in the background on my machine, so this is really just an anecdotal test, but we'll see it. Look at this. We found some order 10s. Think about that. I found in the past, I don't know, 10 minutes I've been talking, I found 2. It's pretty cool, considering Euler searched part-time his whole life and never found them. We'll come back to that. It's not exciting time staring at a blink, and I'm almost done. Oh, there we go. 26 seconds. So the Crystal version took 1/3 of the time just by annotating our code with what actually proves to be slightly better documentation anyway. That seems like an awesome trade to me. So let's go back to my slides and ask. Why would I use it? Sure, okay, I'm in a teaching situation. Speed and clarity matter. That's useful to me. Years before, and it's not gem compatible. It's not like you can take a Ruby gem and download it and use it. There are changes that would have to be made. Years before Rails ever existed, when Addison Wesley was the first publisher of the Pragmatic Ruby book, a friend of mine picked it up. We were looking at it, and we decided to rewrite some Python stuff that we used in a Java build system in Ruby just to learn Ruby. And at that point, Ruby became a better shell scripting tool to me. This was 2001, and I was using Ruby just to write little things that I then run by cron. right? And that solved, I cannot tell you how many literal $1 million business problems I've solved with a rake task in Ruby and cron. Well, every now and then I'd run across a rake task like that where performance would matter. So Crystal would be an awesome choice for that kind of thing. Crystal's evolving very rapidly, and they have a bug bounty program where if you're the person that goes out and modifies the code to support like true parallelism with their concurrency model, you can get paid for that. Everything it outputs to LLVM, which is this intermediate format of a whole bunch of compiler tools. So the optimizing that we get from one benefit of that tool chain applies to Crystal as well. There's all kinds of reason why, if you are a fan of Ruby, Crystal might be the next thing you invest a little bit of time in just to have it in your knowledge portfolio. There's a long payoff, but it's easy to pick up and learn. That's my talk. I have a bunch of different tools I use here for teaching, including some Loudoun code stickers. If you want to talk to me about what a DevOps service area lead means, or just want to argue about what DevOps is, come find me at lunch. Thanks.